So it is required to design the circuit of the 5.52C, and that is the, basically we are talking about voltage divider network to establish a DC drain current ID of zero point 0.5 milliampere. The MOSFET is specified with VT equal to 1 volt and Kn-W by L is equal to 1 milliampere per volt square. For simplicity, we'll neglect the channel length modulation. That is, we'll consider lambda equal to 0. So this is just mentioned, and that equation for in the saturation will be really different. If channel length modulation is there, you need to multiply by 1 plus lambda, VDS. 1 plus lambda VDS, we need to multiply by the equation there. So because we have lambda equal to 0, we'll assuming that, hence we can just consider the equation which we have considered here, right? This equation is generally multiplied by 1 plus lambda VDS when we have the channel length modulation. Because we are considering that we are neglecting the channel length modulation, okay? We don't consider that. We will consider only that equation, okay? Then we will use VDD equal to 15 volts, right? And we need to calculate the percentage change in the value of ID obtained when the MOSFET is replaced with another having the same Kn-W by L but with a VT equal to 1.5 volts. How much is the value of ID? If Kn-W by L is maintained same but VT is changed from 1 volt to 1.5 volts. Okay. So again, as I said, as a rule of thumb for designing the classical Baising circuit, we choose RD and RS to provide 1/3 of the power supply voltage VDD as the drop across each of the RD and the RS, and also the transistor itself, which is VDS, right? So already I explained that in the last class, right? I told that voltage across this is 1/3 VDD, voltage across this VDS is 1/3 VDD, voltage across RS is also 1/3 VDD. So both ID will be flowing here. So to say, IS is equal to ID itself because there is no get current. IG is equal to 0. So ID is the only one which is flowing through this. There's nothing like, IS. IS will be equal to ID. So thus, we can say that RS and RD are chosen same values. RS and RD are chosen same values. Okay. And that is what we are trying to find, that we have 15 volts. So 5 volts across the RD, 5 volts across the RS, and 5 volts VDS is what we will have, right? So we will have the value of VD equal to 10 volts now. The reason why VD is 10 volts is only that the VD means voltage across at the drain, between the drain and the ground, between the drain and the ground. So drain and the ground will be voltage across the VDS plus the voltage across the RS. So this 5 volts plus this 5 volts, that will be 10 volts. So it's not necessary that we should write like that only. We can always write, because of this statement, you can write voltage across RS is equal to 5 volts, voltage across RD is equal to 5 volts, voltage across VDS itself is equal to 5 volts, and hence the value of RD is 5 volts by the value of ID. 5 volts by ID is given as 0.5 milliamperes, hence that will be 10 kilo ohms. Here he has substituted, but this need not be written. You can as well write RD is equal to 1/3 of VDD by ID. RS is equal to 1/3 of VDD by what you call ID. This is ID, not RS. Please remember that this is ID, not RS. So 5 by 0.5 equal to 10 kilo ohms. So both of them 10 kilo ohms. So the required value of VGS can be determined by first calculating the overdrive voltage VOV from the equation. So we generally write the value of this, this VGS minus VT is also known as VOV. VGS minus VT is also known as overdrive voltage, VOV. Okay. So same thing is being used over here. ID is equal to half of K and dash W by L. VGS minus VT whole square is written as VOV square. So ID we know very well, 0.5 milliamperes. K and dash W by L is 1 milliampere per volt square, and half is there as it is, and we will have VOV square. So this is 0.5, this is 0.5, it cancels. So VOV square is equal to 1, so VOV is equal to 1 volt. VOV is equal to 1 volt. And we know that VOV is equal to VGS minus VT. So that means VGS is equal to VT plus VOV, and that will give us 1 plus 1 volt. VT we have taken it as 1 volt, and that's why that turns out to be 2 volts over here, right? 2 volts over. VGS is 2 volts there. Now since Vs is equal to plus 5 volts, Vg must be Vs is equal to 5 volts, then Vg must be here. This we have got it as 2 volts here, this we have got it as 2 volts here, and therefore if this is 5 volts and this is 2 volts, that will give us the 7 volts over here. So this is 10 volts, this is 0.5, this is 5 volts because we have to measure between this and the ground, and because this is 5 volts and we have found that this is 2 volts, this will be 7 volts again. So to establish this voltage at the gate, we may select RG1, is equal to 8 ohm, and RG2 is equal to 7 megohm, right? This is chosen as 8 megohm and this is chosen as 7 megohm because this 15 will get distributed here as 8 volts and 7 volts. And that 8 volts plus, the 7 volts here is what we wanted. Okay. So because this is 7 volts, we are choosing this as 7 megohm. And once this is chosen as 7 megohm, we want the current here to be 1 milliampere because 7 megohm will give me the value of 7 volts here only if 1 milliampere is flowing, 1 microampere is flowing over here. 1 microampere is flowing over here. So to have 1 microampere, naturally this should be 8 because 8 plus 7 will be 15. 15 divided by 15 meg will give me 1 microampere. That's the reason behind this. Okay. Now this is a little direct relationship, which it should have. No, it should not have been like that. But we should try to understand how that is considered over there. So this is 7 megohm and this is 8 megohm because of the reason that you have here 1 microampere. 1 microampere multiplied by 7 megohm will give us 7 volts here. So that is what we wanted. That is what we wanted at the end. So the final circuit is shown in the figure over here. Observe that the DC voltage at the drain is equal to 10 volts. This is equal to 10 volts, allowing a positive signal swing of plus 5 volts, that is up to VDD. So you can have this value can go up when input signal is applied. This value can go up till 15 volts. So signal swing is 15 volts, 5 volts from 10 to 15. That is what he's explaining here. So if the NMOS transistor is replaced with another having VT equal to 1.5 volts, if we in place of VT equal to 1 volt, and if we have 1.5 volts, the new value of ID can be found as ID equal to half of 1 into VGS minus 1.5 square, and this is one equation because VGS will change at that time. It will no more be the 2 volts which we have written earlier. Also, VG is equal to VGS plus IDRD. We will have 7 volts here because of the biasing circuit. So therefore, now this will be 7 equal to VGS plus 10 IDS. So we have two equations, this and this. So two equations, two unknowns, or rather, we can replace the VGS by means of 7 minus 10 ID. VGS, this if 7 is equal to VGS plus 10 ID, VGS will be equal to 7 minus 10 ID. And that 7 minus 10 ID you can substitute in this VGS. So you'll get a quadratic equation in IDS over here. And that quadratic equation in IDS will give us the value of ID equal to 0.455. We might get another value of ID also, but we don't consider that because of the reason that at that time, if we consider that ID value, then the value of the voltage across the what you call uh, the if the ID value is different, then the voltage across this might jump to a very large value. So we don't consider that ID value. Okay, so we'll have to leave one ID value and consider one ID value corresponding to that quadratic equation. Right. So now we have ID equal to 0.55455 milliamperes. Earlier it was the value of ID was, given in the problem as zero point 0.5 milliamperes. So there's a change in the ID. So that change in ID is 0.455 minus zero point 0.5 equal to minus 0.045 milliamperes. And that divided by zero point 0.5 will give the percentage change, and that will be minus 9 percentage change. Okay, minus 9 percentage change. So a different take on that, a different view of dealing with that can be, considered from here also, where same thing is solved. So let us see how he has tried to solve. So again, he has put the same thing. I'm not happy with this equation here, right? RD is equal to, you can just write 1/3 VDD by ID. RS is equal to 1/3 VDD by ID, and that will give both equal to 10 kilo ohms. Having written this he has found it here. This he has found out here. He has just again written the same thing. RG1 equal to 8 megohm, RG2 is equal to 7 megohm for VG equal to 7 volts bias. 7 volts bias. To have a 7 volts bias, here at this point, you need to consider RG1 and RG2 equal to 7 megohm. So percentage change in ID is what we want for VT equal to 1.5. So it's trying to write the equation for 1.5, and again this same thing here. So for both these you'll get this. Rather, I think in the class I might have solved it, and I got both the values of ID. One value of ID is not feasible. This value of the ID is only feasible, and for that we'll get a percentage change of minus 9 percentage. Okay, so let us see one more numerical, right? Let us see one more numerical over here. Consider the MOSFET of again 5.12 when fixed VGS bias is used. Find the required value of VGS to establish a DC bias current of ID equal to 0.5 milliamperes. So earlier what we said, we are ready to allow for the change in VGS, but ID will vary. But now we want to fix the ID. So what should be the required value of VGS to establish a bias current of ID equal to 0.5 milliamperes? Okay. Recall that the device parameters are VT equal to 1 volt, Kn dash W by L is equal to 1 milliampere per volt square, and lambda is equal to 0. What is the percentage change in IT obtained when the transistor is replaced with another having a value of 1.5 volts? Okay, so now this is a fixed VGS over here. The equation, if you see there, is 5.12 with a fixed VGS bias is used when fixed VGS bias is used. So fixed VGS bias is used just gives us the figure which corresponds to the one which is here. Okay, we have not shown here. Fine, no problem. Only that we need to consider the what you call fixed VGS will give us that there is no RS at all. Okay, so when there is no RS, what will be the value of the what you call uh, value of VGS we want there. Okay, in the to establish a DC drain current of ID equal to zero point 0.5 milliamperes. Okay, if we want zero point 0.5 milliamperes, and we consider what you call in the example which we have considered in the earlier case itself, right? So MOSFET in the 5.12, 5.12 is, where is 5.12? This is 5.12, right? Fixed VGS bias is used. Find the required value of VGS to establish a DC bias current of ID equal to 0.5. So VGS, we already found that it will be equal to 2 volts. So sorry, we should consider this, you know, what you call the same circuit which we have used in the earlier example. So at that time, the value of VGS is equal to what you call 2 volts. The value of VGS is equal to, we have already found out that the value of VGS is equal to 2 volts. VGS is equal to 2 volts is what we have found out. In the same way, that means same steps we should follow to get the value of VGS is equal to 2 volts. Okay. So for this value of ID, with VT equal to this, you can just substitute in the equation VGS, ID is equal to what you call half of Kn dash W by L VGS minus VT whole square, right? So VT is given as 1 volt, right? ID is given as 0.5, and we can need to find out the VGS, and that turns out to be the value equal to 2 volts. Okay, we'll get it as 2 volts. So from that, once we find the value of the VGS, we find the value of VDS. So equation to be used for this is the same equation which we have written here, right? So ID is to be substituted, VT is to be substituted, then the value of VGS is to be found for, whatever is this Kn dash. This is nothing but Kn dash, right? Kn dash W by L. Kn dash W. This is Kn dash. Mu n COX is itself Kn dash, right? So this will be Kn dash W by L is what is given. VT is given, ID is given, VGS is to be found out, right? VGS is to be found out. So corresponding to that, now, now he is telling that use a power supply of, sorry. So now, if the value once VGS is found, the next thing is, if VT is changed to 1.5 volts, what is the value? What is the percentage change in the ID. So what is the ID obtained and what is the percentage change, right? So for that, we need, for the new value of ID, again, we need to substitute in the earlier expression only. That is, now VGS is equal to 2 volts only, and now VT will be equal to 1.5. What is the new value of ID? We need to find that. Having found the ID there, right? So this is 2, this is, 1.5, Kn dash W by L same. Find the value of ID now, and the difference in the two IDs divided by the original ID will give us the value of the percentage change. The value of the percentage change, right? And that value turns out to be minus 75 percentage, minus 75 percentage. Are you with me? Is it clear, or is there any doubt here? People are saturated. So that is the problem to be solved. So now we can take up the next one. So he's talking about E over here. E is the circuit which will correspond to two. I think E in the where is he? Yes, E is this. So that is two power supplies are there over here. Two power supplies are there, right? So when two power supplies are there to operate the DC, to operate at a DC drain current of 0.5 milliamperes, VD equal to 2 volts, let VT equal to 1 volt, K dash W by L is equal to 1 milliampere per volt square, lambda equal to 0, VDD and VSS both are 5 volts. Use standard 5% resistor values. See appendix G, he says, and use the and give the resulting values of ID and VD and VS. Okay, so uh, we need to find out the value of ID and VD and VS corresponding to this resistors. Okay, so straight away we can try to find out the value of the you know so to say ID and VD and VS. We are given with VD equal to 2 volts in the figure E, which corresponds to this. Yes, this is E. So the potential here is 2 volts. This is 5 volts. This is minus 5 volts, right? The potential here is 2 volts. So now we can try to find out the value of the ID given to us the value of the okay. So I think we are given with the value of the ID itself, which is zero point 0.5 milliamperes. For this zero point 0.5 milliamperes, what is the value of RD? We can find out first, and then later, that resistor, is it available to us? Is a question which will arise, and because that is not available, we need to choose somewhere nearer which is available in the what you call uh, somewhere which is available in the appendix G, whatever is available. So for this value of zero point 0.5 milliamperes, if we go back to that, right? So VDD is equal to, RD is equal to this voltage VDD minus VD. VD is 2 volts, 5 minus 2 divided by ID. RD is equal to VDD minus VD divided by ID. So ID is zero point 0.5 milliamperes. 5 minus 2 divided by zero point 0.5 will give us the value which is equal to uh, 6 kilo ohms. 5 minus 2 divided by zero point 0.5 will give RD is equal to 6 kilo ohms. But 6 kilo ohms might not be available in the 5% so to say values. Let us see what is available in the appendix G. In the appendix G, what is available? Let us try to see that. So this is the appendix. I think appendix G is quite far off away. Yes, this is the appendix G. G1, we should be able to go very much far. Yeah. Oh, this is the appendix G. He is telling appendix G. Is it appendix G or resistor values? Oh, yes, he says here appendix G, but that doesn't seem to be appendix G. Here he has bibliography. Where is the resistor values? No, not here. Standard resistance values and unit prefixes. Here it is all right. Why there it is not showing? Should I kept it ready? Might be that would have been better. F is domain false. G is history. Okay, here it is appendix H. Yes, mixed up things. Okay, so this is 1% resistor value. This is 10% resistor value. So what is available? 6 kilo ohms is not available. You have here 62. So 62 means we should use 6.2. We should use 6.2, right? So what is available to us is 6.2 kilo ohms, right? 62 is not available. 6.2 kilo ohms you should use. So once having used 6.2 kilo ohms there, then what will be the value of ID? Again, we should reverse, find back the value of ID. That is, ID is equal to VDD, again minus VD, that is 5 minus 2 divided by 6.2. So some difference in value of ID, you'll get it there, right? So using that, we can find the value of VD again. Okay, we can use the value of VD again. So like that we should give, I think I have solved it there. So RD is equal to RS is equal to 6.2. ID, you'll get it back as 0.49 milliamperes corresponding to this value of RD, right? The way to find would be, I think we should see that VD also will change. So both ID and VD will change, we should assume. So we'll have two equations might be at that time. So for that, you need to find out that and solve that, right? So one equation might be VDD is equal to VD is equal to VDD minus IDRD, where both VD as well as the ID should be unknowns. The second equation would be ID is equal to half of Kn dash W by L, VGS minus VT whole square. And VDS minus VT VGS can be again found out in the same way. And we can have two equations for, the solving, and then we'll get that. So we'll get here the value of Vs as well as Vd somewhere at 1.96, the value of that, and we can select the value of Rg in the range of 1 megohm to 10 megohm. So that's how we can solve this equation. I hope I have solved that in the class also. Just check it up. So with this, we'll try to stop in the recording and the class.